Good afternoon. So today I will be reporting about electrical characterization, particularly principles and a case study about doping and carrier densities. So this is the outline of my presentation, introduction, then let me pointer. So introduction, we will start with the introduction. Then we will deal with the derivation of the doping density equation. Then I will be discussing about the importance of depth for doping density. Then from after doping density, we will also be discussing, I will be discussing about the derivation of carrier density. Then after that, I will be highlighting a very important concept about the derivation from the previous parts in distinguishing carrier versus doping density. Then I will also have a brief discussion about band offsets and a case study about carrier and doping densities in semiconductors. So introduction, electrical characterization is a very important practice in the industry, particularly semiconductor industry. It is composed of essential techniques which determine material properties in the form of true electrical concepts. So these methods are primarily used to assess quality of semiconductor materials. So quality in terms of manufacturability, process optimization, or exploratory studies. So this is from a perspective of the industry. So we see electrical characterization for these purposes. So these are the main uh, drivers of the importance of electrical characterization in the industry. So in this presentation, the focus topics are the determination of carrier and doping densities by differential capacitance. So I will be discussing about the theoretical concepts and a case study. So this is just an overview. This is the sample material to the FETs. So this is an overview of the electrical characterization methods. So this is a more detailed breakdown. So I will be dealing with carrier density. So carrier density is the number of charged species per unit volume. It is usually expressed as per meter cube, or actually the per meter cube can be converted to other units of volume. Doping density is the concentration of dopant per unit volume. So it is commonly expressed as atomic weight percent or molar parts per million ppm or percent by weight ppm weight percent. So these quantities, the two, carrier density and doping density, are commonly interchanged, but they have important difference. They have distinct difference. And this difference can be determined by electrical characterization methods. So here, this is for carrier density. The common electrical methods for determining carrier density are current voltage, capacitance voltage, Hall effect, and spreading resistance. For doping density, we have SIMS, FIB, IR, and photoluminescence. So the focus of this presentation is about capacitance voltage. So let's first derive the governing equations for doping density. So the fundamental principle of capacitance voltage technique relies on the dependence of the width of the space charge region on voltage. So you have consider a Schottky barrier diode, which is a p-type semiconductor with doping density Na. So the derivation starts with applying a DC bias with a voltage capital V to produce a space charge region of width W. So this is the equation for the differential capacitance. QM and QS are the metal and semiconductor charges respectively. So aside from the DC bias, we will also apply a voltage V, a small v, an AC voltage. So the AC voltage increases from 0 to a small positive charge dQm, which corresponds also to an increment of semiconductor charge dQs. So this is the setup from taken from Schroeder. So this is the reverse bias Schottky diode, and this is the concept, the starting variables for the derivation of doping density and majority carrier density profiles. So I will be dealing with that later. So this is the equation for the semiconductor charge from here. So I will not be dealing with the mathematical aspect of this. So this is the expression. Okay, so the important assumptions here are the depletion approximation. So we have this as approximation. Also an assumption that all acceptors are ionized. So using equation 2.2 in 2.1, we can derive the equation for capacitance, which is in this form, equation 2.3. Again, another assumption here is that the doping density, Na, does not vary over the width of the space charge region, the dW. So as you can, this is implied from the unit of the resulting quantity here, which is expressed in farads, not in farads per square centimeter. So this is the limitation of the CV method in measuring doping density. So let's consider a reverse bias junction. So similar to this previous derivation. Now let's consider the factor, the area factor. So given a parallel plate capacitor, the capacitance is given by this formula. So Ks is the dielectric constant. Epsilon naught is the permittivity in vacuum. So A is the area of the capacitor plate. So as we differentiate 2.4, equation 2.4, we can derive the equation for doping density as a function of the space charge region, the width of this space SCR. So this is the, actually this is the important equation that we need to remember. So we have this equation. From here, you can see that there is that the C variables are in the denominator and actually expressed as dC over dV and d of 1 over c squared over dV. So this identity was used to derive this second expression of equation 2.5. Okay, so this is a summary of the important relationships we got from equation 2.5. Note that equation 2.5 is actually a linear function wherein we can plot the CV curve and 1 over c squared V curve, wherein the slope is are as follow. So for CV, it's dC over dV. For 1 over c squared V curve, it's d over 1 over c squared over dV. So this is the slope. The slope is equal to the doping density. So equation 2.4, so these are the important equations. So from here, we can actually now measure doping density from experimental data, from the capacitance voltage data. Now, let's extend this concept, same concept. Now we are dealing with depth of doping density. So it is important here that aside from the area of the sample, we need to also assess the depth. So here it is also expressed in terms of expressed as W. So W here is associated with depth at which the doping density is evaluated. So the depth is important factor in doping density equation. So for this equation to hold true, to be true, uh, and in relation to the factor of depth, the following must be satisfied. So first, the space charge region spreading must be negligible. Then for the junction, the doping density of the concentration of the heavily doped side must be 100 times or more than the other. Unless or else if the junction somehow equilibrates with less than 100 times concentration of dopant, then the equation here will not be, there will be a significant deviation. So in most PN junctions, the depth conditions are applicable. In some cases, however, there are factors which affect the accuracy of the previous equations. So for instance, for MSE and MOSFETs, it is influenced by the generation of interference traps and minority carriers. In such case, the equation here should be modified to account for the species which interfere in the depth of the doping density evaluation. So here the term 1 over C sub ox, which stands for the oxide capacitance, is incorporated in the equation. So to account for the other factors which affect the depth of the doping density. Now, this issue can easily be overcome by providing a minority carrier sink. So these charge carriers are avoided by providing a source or drain voltage equal or higher than the gate voltage. Another workaround is the use of contactless capacitance and doping profiling. So it is actually a setup that makes use of a sensor electrode about 1 millimeter in diameter and coated with high dielectric strength thin film. So, and it is surrounded by a biased guard electrode. So this sensor electrode is held above the wafer by a porous ceramic air bearing, which is very stable with respect to the position of the wafer. So this setup, it makes use of air as a cushion or a spring that prevents the porous surface from touching the wafer. So in this case, actually, it will be C sub air. Using the point of this is that we can make use of other experimental setup as long as we make the necessary change in the computation of the W. So here it should be 1 over C sub air because we make use of air as the interfering layer. So this is the setup of contactless doping profiling arrangement. So now that's for doping density. Now all the previous discussion that I had elaborated actually lies on a very important assumption, which is all those equations or the conditions in which the measurements are taken follow the depletion approximation. So all the relationships here that I discussed, this one, equation 2.7, 2.6, especially these 2.4 and 2.5. These are true if the conditions are following the depletion approximation, which in most cases, in most experimental setup, are not following. So actually, what we measure from CV technique is the not the doping density, because depletion approximation is very hard, is a very uh, ideal assumption. So what are these conditions? So first, the sample must have homogeneous doping. Then in the previous equations, we also neglect the presence of the minority carriers. Also, we are not considering the depletion of major carriers in the SCR at depth W. Also, we assume that there is a perfect charge neutrality beyond SCR. So if any of the conditions above does not hold true, doping density profiling is not applicable. So all the equations I have discussed are not applicable in measuring the doping density. In most cases, it does not apply. Instead, what we are measuring is the carrier density. So actually, to be specific, it is the effective carrier density, not the true carrier density or the doping density. So these are the governing equations. All these equations are actually not measuring doping density, but the effective carrier density. So again, these are the crucial expressions that we actually use in data analysis. So same form, dc over dv and d over 1c squared dv. So these are equal to carrier density. So let's talk about these two. So in practice, CV data are usually obtained in terms of 1 over c squared v instead of CV, because it is more direct or easier to use in data analysis. The former plot, the 1 over c squared v, can easily show the uniformity of the carrier density based on the slope. So as you can see here, this is the 1 over c squared. You can easily see here the linearity of the function. Then there is a discontinuity around 3 volts. So here, the linearity is not following anymore. Unlike here, unlike for C, that is usually expressed in exponential function. Also, the slope here, as I mentioned a while ago, is more complex to obtain than for this one, for 1 over c squared. So this is the carrier density profile calculated from these equations. So again, as I'd like to emphasize that what we are measuring from CV technique is the carrier density and not the doping density. Now let's go to the deviation of doping density from carrier density. So as mentioned, one of the conditions in the depletion approximation is that non-uniformity of doping is a differentiating factor that invalidates doping density in most CV measurements. So we have actually experimental data to prove that. As you can see here, P is the majority carrier density, and Na is the doping density. So also here, it is important to also distinguish the effective carrier density versus the true carrier density. So here, actual is the experimental data, the broken lines. Then the calculated P, or the calculated carrier density, is this straight line here. So you can also see that there is a observable deviation. So as mentioned, non-uniformity of doping is one of the factors that invalidates doping density. So in fact, what we measure is the effective carrier density. Also, we are not measuring the true carrier density, not aligned with the experimental data. So the deviation of the doping density from majority carrier density is defined by the D by length. It is expressed as LD, or it is the distance over which charge imbalance is neutralized by majority carriers under steady state or equilibrium condition. So this is the equation. The D by length is also the limit of spatial resolution, meaning capacitance is highly dependent on the movement of the majority carriers, which in turn is dependent on the spatial changes of the sample. So if the doping density, if the spatial characteristics of the sample is not as uniform as assumed, then that factor is the D by length. So this is just an equation, derived equation to correlate carrier versus doping densities, just to test the how much the deviation is. Again, the depletion approximation here proves that there is there's a significant deviation between the two quantities, and here it proves that even computer simulations show that this equation is too much of a simplification. So in Schroeder, there are some cases were given on about the common problems in correlating these two quantities. For example, for low-high junctions, the results highly depend on whether the junction is profiled from the P negative or P positive side. So a step simulation show that a step profile cannot resolve when the D by length is 2 to 3, less than 2 to 3 LD. A doping density ramp profile is not distinguishable using 2.12 unless it is at least it is more than 1 D by length. Also, most of the examples I have given in this presentation are reverse biased junctions. So for zero or forward biased Schottky and PN junctions, usually this equation, the correlation between carrier and doping densities cannot really be established by one governing equation. So this is just another graph to show or to highlight the difference between these two quantities. So solid lines are experimental data or the doping density. The dashed lines are the absence of interference rates. So it is quite over this one. And the dashed lines is the profile when depletion approximation is used. So solid line, this is the experimental data, and this is when depletion approximation is used. So as you can see here, there's a clear difference. So band offsets, this is just another concept that was discussed that is discussed in Schroeder, because it is also measurable by CV techniques. So when two semiconductors with different band gaps are combined, conduction and valence bands cannot be aligned. So this is called band offset, or it may exist in the conduction band, valence band, or both. So band offsets can be measured by infrared absorption, photoemission spectroscopy, or CV methods. So common samples with band offsets measured by CV are NN, PP isotype heterojunctions. So lowercase np refer to the semiconductor with narrow band gap. Uppercase NP for wide band gap. So band offsets can be related to doping density. This is the equation. ND of X is the uh, ND of X is the doping density. So this is just a diagram of band offset. As you can see here, there is two sets of conduction and valence band due to the distinct difference between the two semiconductors. So the CV and 1/CV curves are shown here. The doping density profiles are determined from M1 and M2. So this one and this one. The plateau capacitance CPL is related to the thickness of the narrow band semiconductor, and the plateau voltage VPL is related to the band offset. So here, okay. So that's for this diagram. This is just another diagram that shows the band offset in terms of doping density. So a plant of apparent carrier density of a gas, N-gas and N-al-gas heterojunction. So here, the experimental data are the straight line. Sorry, the points here, this one. Then the straight line is the assumed donor density. So let's go to the case study of using carrier and doping density concepts in semiconductors. So this paper was published last 2018. It is ECV dope entitled ECV doping profile measurements in silicon using conventional potentiostat. So this paper is a very straightforward one. The authors aimed to apply CV measurements to improvised electrochemical cell with the potentiostat and EIS module. So in this case, they fabricated a improvised setup that makes use of common laboratory electrochemical laboratory apparatus, and they assess the accuracy of the data that they can get from this improvised setup using dopant profiles. So the methodology, here are the materials: 440 micron thick P-type silicon wafer, cleaning solution made of hydrofluoric acid, acetic acid, and nitric, and diluted orthophosphoric acid in 8%, 12%, and 15% as the dopant. So this is the methodology. The wafers are first prepared, diced into 2 cm by 2 cm, chemically cleaned by immersion in the this cleaning solution in this ratio. Then the 3 p-dope silicon samples were prepared by spray deposition using the 3 different concentrations of orthophosphoric acid. So these are the parameters of the spray deposition. All experiments were carried out in atmospheric conditions. Then after deposition, the samples were annealed, dried at 200 degrees Celsius for 20 minutes to create the P2O5 layers as governed by these chemical reactions. Then the P diffusion was carried out in a tube furnace at 910 degrees Celsius for 47 minutes with N2. Then these are the profiler equipment. Then the electrochemical solution is this one. This is the CV contact. So this is their setup, the improvised setup. These equations are taken from the paper. So we can see here the similarity with what discussed in Schroeder. So same equations, just different variables were used, but it is essentially the same. So these are the results of the dopant profiles obtained using CV measurements. So in this case, they used 1/c squared. So here, figure 4.A to C indicates that the value of 1/c squared increased with the bias voltage. So as we as we decrease, actually, as we decrease the voltage, so the 1/c squared value also decreases. So with the depletion region depth increasing according to equation 2. So this one, this one, WD. The depth of the depletion region increased because the positive and negative ions become more separated as the reverse bias voltage was applied, leading to an increase in WD. So this one. On the other hand, by decreasing the capacitance, the electrical impedance also increased. These results show that as the slopes of the curve increase in each step of the Schottky test, the doping concentration decreased. So according to equation 1, so this one, this is the concentration. It is inversely proportional to 1/c squared. So the results of the CV test for the 8%, so this is the 8%, this is the 12%, and this is the 15% dope silicon, did not reach the junction diffusion depth since the slopes of the line of the adjacent steps were not equal. So by the way, for 15%, you can see here that there is a discontinuity, meaning doping, the spatial resolution here, or the deep bilent, was already affected by the increase in doping concentration. So this is the correlation of the accuracy of their setup versus a calculated doping concentration. So they obtain somehow fair results. Their CV data are comparable to the calculated ones. So these are the R squared values, which are found to be close to the calculated measurements. So in here, they suggest that, for instance, the junction diffusion depth was calculated to be 0.7 for the developed setup and 0.77 for us calculated by the ECV profiler. So that's a very close result. So in summary, we were in this presentation, doping density was derived using differential capacitance. Then we obtain the plots of the CV and 1/c squared V, which we correlated with doping density. Then we also deal with the importance of the depth of the sample in doping density measurements. So after doping density, derivation of doping density, we found that all those measurements are only true due to the depletion approximation. But in actual, this assumption is not true, is very idealistic, and in actual, this does not happen. And what we actually measure is the majority carrier density. There is a really significant difference between carrier and doping densities and cannot be modeled without accounting many factors. So I have enumerated some of the common problems encountered when calculating the deviation between these two quantities. So we also discussed briefly about band gap offsets, and I presented a case study on how dopant measurements, CV measurements are used to validate the accuracy of a fabricated setup compared to the calculated one. So answers to guide questions. So how is the capacitance measured? So I've discussed this a while ago. The semiconductor or a Schottky diode is subjected to DC and AC voltages. Capacitance is calculated as the width of the SCR. Why is 1 over C squared V preferred over CV? I've mentioned this also. It is because of the easier data analysis in using 1 over C squared. What is measured in most profiling techniques? So it is the majority carrier density. I've highlighted this, that doping density is not applicable to CV measurements because of the depletion approximation does not happen in real life. What is the D by length? So it is the measure of the deviation of doping density versus majority carrier density. So references. Thank you.